All right, let's dive into this explainer. Today, we're building a rigorous blueprint for exactly how clinical researchers select their study populations. The line between a massive medical breakthrough and a quietly retracted paper almost always comes down to one single thing, and that's population selection. A poorly sampled study gives you completely useless data, while a masterfully sampled one hands us universally actionable medical truths. So, we're unpacking the advanced science of sampling techniques. We'll explore the precise methods researchers use to gather robust data, and most importantly, we're going to see how applying three very specific steps can drastically improve the output and the validity of your next research project. Here's a quick look at our agenda for today. 1. Why sampling matters. 2. Probability sampling methods. 3. Non-probability sampling methods. And 4. 3 steps to better output. Starting off with Section 1, Why Sampling Matters, the foundation of feasible research. So think about this for a second. How do you actually test a brand new drug on an entire country? Unless you've got an infinite budget and a literal time machine, testing a new antibiotic on every single citizen is completely impossible, right? We absolutely have to have a mathematical shortcut to make large-scale medical research even feasible. And here is that brilliant, statistically sound solution: 500. By using a rigorously chosen, highly representative sample of just 500 people, researchers can unlock incredibly valid, actionable results that apply to millions. That number represents the absolute magic of statistics. It makes massive research practical. But here's the catch. You can't just pick any random group of 500 people. How you select them literally dictates the integrity of your entire study. We basically have two main toolboxes to pull from here. On one side, we have probability sampling. This is the rigorous gold standard where every single member of a population has a calculable chance of being selected, which systematically strips out bias. On the flip side, we've got non-probability sampling. Here, selection is based on human judgment or just plain convenience. You're trading that perfect generalizability for practical speed and much lower costs. Let's look closer at Section 2, Probability Sampling Methods, the rigorous gold standard. The bedrock method in this toolbox is simple random sampling. Just think of it like a giant lottery machine. It gives every single patient an absolutely equal chance of being selected. A great real-world example would be randomly picking 100 hospital patients from a massive centralized database to study their adherence to hypertension meds. There's zero human bias in who gets picked, because the numbers decide. Now, the crucial point to remember is that this specific method works beautifully, but really only under certain conditions. It's best used when you have a complete, totally accurate list of a large, very similar population. But beware, if your database is suddenly glitching and missing half the hospital's patients, well, your simple random sample suddenly isn't so random anymore, and your data's fundamentally compromised. To handle more complex populations, we pull out systematic or stratified sampling. Systematic is exactly what it sounds like. Imagine standing at a pharmacy counter and surveying every 10th patient who walks up for a consultation. It's highly ordered. But right next to it is stratified sampling, which is just a powerhouse. Let's say you want to study insulin usage. You wouldn't want a completely random mix because age plays a massive role there. So you divide your population into strata or subgroups, ages 18 to 40, 41 to 60, and 60 plus, and then you randomly sample within those specific buckets. That guarantees that all the different life stages are perfectly represented in your data. But what if your population is spread out across an entire state? Doing a simple random sample might require you to drive to 50 different towns just to interview one person in each location. That's a nightmare. That's where cluster sampling comes in. You utilize naturally occurring groups. Instead of picking individual pharmacists across a huge region, you randomly select 10 entire community pharmacies. Those are your clusters. And then you survey every single pharmacist within those 10 locations about dispensing errors. It's wildly cost-effective and saves researchers countless hours. Moving on to Section 3, Non-probability sampling methods, the practical approach. Over in this toolbox, selection is based on judgment or convenience, not strict mathematical chance. With convenient sampling, you're moving fast, grabbing whoever is most accessible, like firing off a drug interaction survey to whoever happens to be sitting in the pharmacy waiting area on a Monday morning. Is it perfectly representative of the whole town? Definitely not, but it gets you data quickly. On the other end is purposive or judgmental sampling. This one is highly deliberate. If you want to understand antibiotic stewardship practices, you wouldn't ask random people. You would purposefully track down and interview only senior clinical pharmacists because you specifically need their rare specialized expertise. For really highly specialized scenarios, we look at snowball versus quota sampling. With snowball sampling, you're studying something incredibly rare, like patients taking orphan drugs for unusual diseases. You can't just find them in a random directory. You find one patient, and they recruit others from their private support networks. The sample grows organically, just like a snowball rolling down a hill. Quota sampling, on the other hand, is a lightning-fast way to hit specific demographic targets. If you need exactly 50 male and 50 female patients for a pharmacovigilance study on a new drug, you simply set that quota and recruit until those exact slots are filled. No randomized selection to worry about. Which brings us to Section 4, 3 steps to better output. This is all about choosing the right method. Okay, having the tools doesn't automatically make you a master builder. By following this exact 3-step blueprint, you will dramatically improve your research output. Step 1, choose your method by matching it directly to your study question. Are you looking for broad national trends or niche expert opinions? Step 2, rigorously assess your resources. What's your actual budget? How much time do you really have? Do you truly have access to a full population database? Step 3, define your ultimate goal. Do you need perfect generalizability, or do you just need speed and exploratory data? Literally walking through these 3 exact steps prevents researchers from wasting millions of dollars on a badly designed study. To summarize that decision matrix from our 3 steps, use probability sampling for your high-stakes scenarios. When you're running clinical trials or testing drug efficacy, low bias is critical. You need absolute certainty that the results apply to the real world. But use non-probability sampling when you're constrained by time and budget, like during pilot studies or qualitative research where you're just trying to understand the landscape before launching a massive, expensive trial. If you take nothing else away from this explainer, this is the ultimate golden rule. The quality of your output isn't about always using the most complicated statistical method, it's about alignment. Always match the method to your research question and the resources available to you. Whether you're designing a tiny pilot study or running a massive multinational trial, producing solid research always starts with your initial design. I want to leave you with a thought to really challenge how you consume information going forward. The next time you see a massive medical breakthrough or a scary health statistic headlining the news, don't just look at the shiny result. Stop and ask yourself, how were those participants actually sampled? Was it a massive randomized trial or a convenient sample of a dozen people? Understanding that difference completely changes how you see the world of medical research. Thanks for joining me on this deep dive.